Hello, I'm going to show you a stipulation of something in special relativity called length contraction. Now, length contraction, what happens is if any object travels towards or away from you, or any velocity relative to the speed of light, then its size contracts. Its length contracts in the direction of its movement. Also, in special relativity, there something came about called the twin paradox, and the twin paradox is it's a paradox resulting of the speed of light. So what I have here now, the twin paradox is obviously it's actually real. It's an actual real paradox, but in the twin paradox, they use two clocks to explain a paradox. In this video, I'm going to show you how you use two different length contractions or two different objects that length contract to prove that the twin paradox is a real paradox. So what I have here is I have two rocket ships. I have rocket ship A and rocket ship B, and they both accelerate away from each other, and the total combined speed is somewhere near the speed of light. So from A's observation, this entire experiment has to be from a particular point of view. So from this experiment, we have observer A. And observer in this rocket ship, we have two triangles at the rear of the rocket ship. These aren't flames, these are just triangles. And on B's rocket ship, we also have two triangles. Now, both ships are exactly alike before they ever started the experiment. However, from observer A's point of view, he observes that rocket ship B length contracted. So I have here rocket ship length contracted and time dilated. Now this is from observer A's point of view. So from observer A's point of view, their rocket ship, nothing length contracted because they're going the same speed as observer A. However, rocket ship B, the length of their ship contracted and the triangles contracted. Now to prove this, observer A and observer B are going to shoot out laser beams. And so from observer A's point of view, observer B shoots out a laser beam, and it travels and travels until it hits these triangles. And it hits a triangle and hits a 90-degree angle, and it goes down 90 degrees. And it hits another triangle and goes back 90 degrees. So from observer A's point of view, that's what happened. And also from observer A's point of view, it shot a laser beam out, but instead of the triangles being like these, 90 degrees, they're like 30-degree triangles. So what happens, instead of the laser beam hitting this triangle and going back down to this one, it didn't even do that. It hit this triangle and made this trajectory here. So the thing of it is the paradox exists is if you switch observers. So instead of this being observer A, because this is all from observer A's point of view. From observer B's point of view, the exact same thing exists. So we have two different realities here. So now from observer B's point of view, the laser beam comes, hits the triangles, and bounces back to observer A. From A's point of view, it doesn't do that. From B's point of view, A's rocket ship doesn't do that. So we have a paradox. It depends on the paradox depends on which observer's point of view we're looking at. It could change the entire reality for each observer. For example, let's say that if this laser beam does do a round trip and comes back and hits A explodes, and A is dead. So from B's point of view, A is dead, right? But not from A's point of view, because we just have to switch rocket ships. From A's point of view, B is dead. So it depends on the observation. So, you know, what is it? Is A and B both alive and dead, or is A and B both dead? So it's a paradox, and it really depends on your observation. And this proves the twin paradox, or it proves that the paradox is real.